So today, what I wanted to talk about was this topic that I was kind of starting to look into in my spare time, which is graph neural networks. So there, this I feel pretty exciting application of deep learning because instead of operating over data that's just like vectorized data, or like let's say like the typical stuff we usually work with in machine learning, like images, like text. Instead, you're working with graph-like data, and sort of there's a bunch of applications here. So uh, yeah. So I would say that there's two like main ones that I can talk about. So let's go here. Uh, so the first application is like drug discovery, essentially because a molecule is a graph, and I'll describe that in a second. And then the second application is more around like social networks or networks of people. So this is large graphs. I'm not going to talk about this today, but I'm mostly going to talk about like molecules and drug discovery. But everything that I talk about for small networks should apply very naturally to the large networks. So let's get started. So first off, like I told you a molecule is a graph, but let's look at this point a bit more deeply. So let's look at H2O molecule, for example. Right. So yeah, so this is sort of the graph structure. So you'll see that there's like atoms. So those are the nodes. And then there's edges, and that those edges also have specific features, which are angles. And so in this case, like not only do you have node level features, like you also have edge level features. So there's both. So any sort of graph framework that we want to operate over is going to be the same. And so the data set we're going to be working with today is called QM9. And so let me just show you this data set, the QM9 data set. Oh, it's on Kaggle. Okay, great. I'll show it to you here. Scalar coupling. What are these guys doing? So can you measure the magnetic interactions between pairs of atoms? All right. So for example, like that could be one sort of supervised learning task. Like you're given pairs of molecules and you're tasked with finding like what is the magnetic coupling between them. So that's just like one problem formulation. But if I should show you the full data set, and how big is this thing? Oh, it's like in a MATLAB format. Interesting. Okay, so I think Spektral has a way for us to download this data set. So let's just check it out in Spektral. Let me just briefly talk about the Spektral library. So sort of as a general framework, like, we talked about this. I'm just going to draw something for you real quick. Hey, how's it going, Hoda? So just to talk about this like very quickly, where was this here? So we said like we're going to have like a bunch of these molecules, like let's say like H2O. And so our goal is to then take this molecule and then feed it to some sort of deep learning algorithm. So this is what Keras will do. So I'll type here some text. So I'm just writing a box because you can just think of this as some sort of like box model. And then this is going to do some prediction on this. So here, for example, we go out here, we have this. And then as an output, like we can do a bunch of stuff. So for example, we could do like in typical fashion of any sort of deep learning problem, like, that you could do classification. So an example of this is, let's say, is this molecule toxic? One moment. Yeah. Yeah. So is this molecule toxic? Is it soluble? Etc. Another one is regression. So in regression, it's sort of a similar, like sort of sister problem, but as opposed to trying to predict like a binary outcome, like true or false, or which category does this belong to, you want to ask like how toxic is it? How toxic is this molecule? From like 0 to 1. And then the third one could be some sort of generative task, which is generate a molecule. So generation is especially important for tasks like discovering new drugs. finding new drugs that are similar to drugs that we know that are safe but may have different effects. And so this is sort of the general framework and, why I believe you should care about this problem. So how does this happen? So we know that once something, let's say typically in a lot of deep learning algorithms, we generally know that if we can fit a vector to a Keras model and get a vector out, then this is all easy. Like we understand how to do this. And so let me just draw a quick picture. So let's assume I have a vector that looks like this, and then maybe I'll draw some lines here, because these are just let's say, yeah, so we have some sort of vector here, and then our goal is to take this vector, let's say, and then feed it to the Keras model. Right here. Okay, I don't know why part of this was chomped. Let me just fix this. Yeah. So we want to feed this to Keras, or any sort of deep learning library that we're working with, and either we want to get a classification. So in that case, we want to, let's say, predict 0 or 1, or we want to predict a regression. So in this case, it would be, let's do the 3 arrows. And then, yeah, like I said, so either, let's say, we predict a value 0 to 1. So this would be the regression task. Or we want to do a generative task. So in which case, we basically predict another vector. Right? So if you know sort of the basics of machine learning, none of this looks really surprising. This is all stuff we should understand how to do it. And if you don't, let's just ask me questions and I can talk about it in more detail. Or just check out some of my other talks on the topic. And so what does a graph neural network library do then? So the main responsibility of a graph neural network library is to figure out how do we turn a vector, sorry, like a molecule or a graph. I'll draw a new one. So let's go to scribbles. Yeah. So how do we turn a molecule into a vector, or a graph into a vector? How does this work? And I'm putting both arrows because those two representations should ideally be the same, right? We want our representation to fit. So, and this is sort of the main this is sort of the main problem that Spektral solves. This step of how do I turn a graph into a vector, so then I can just feed it into any sort of deep learning algorithm I have to actually make some sort of useful prediction or classification or regression. This is the main job of a graph neural network library. So how does this work? So, well, but before I talk about how this works for a graph, let's just think about how this works in more generally. Let's say you had some textual data, right? And let's say it was you had dog, and these are, let's say you're trying to predict some sort of classifier, and then you have cat, and then let's say you have mouse, for example, right? And so one reasonable heuristic is you could just come in and you assign an integer value for each of these. So for example, you could just say, well, dogs, that corresponds to 1. So this is just 1. And then cat, that corresponds to label 2. And then mouse, well, that corresponds to 3. Right? So this is sort of the most basic way when we think about how do we transform something that doesn't seem like it can be understood by a deep learning algorithm into something that can. And so, great. So this is sort of the simple case, but ideally, when you think about this representation, in some sense, when we think about word embeddings, for example, in the NLP community, let's say this was house, for example, or I don't know, let's say this was house. Well, ideally, I want the label of house to be very far away from the label of mouse, because I sort of have this implicit understanding that houses aren't very similar to mice, whereas dogs, cats, and mice, well, they're all mammals. And so I want their vectors to be similar. And so as opposed to just having integer, we end up with vectors that somehow compress the meaning of this thing. So like I said here, you come in here, and then, you know, this would be a vector. So this is how I'm representing vectors. And you would do the same thing for each of these. So like I said, so this is sort of the vanilla use case. So great. So now that we've sort of discussed the high levels of how this works for words, like how does this work for graphs? So in the case of a graph, like you have a couple of features that you need to think about. So let's draw our H2O molecule again. I mean, let me just actually show it to you here. So if you look at the H2O molecule, like we said, well, first off, we have these node level features. So it's like, which atom is it? Then we have these edge level features, like which angles is it? And then you have some neighbors. And now the molecules can be more complex than this. Like this is a very simple molecule where, you know, oxygen is connected to everything. However, like let's just look at like a longer molecule, just so you can understand the difference here. So yeah, for example here. So if you look at a longer molecule, for example, like this is sort of a similar idea, like, or let's say something like this with the cool handwriting. So you'll notice that there's like some node level features, some end level features, like some of the nodes here themselves are molecules, so you could further expand out this representation. But regardless, there's sort of a simple trick you can do here. So on one hand, like, you know, like word tasks we're thinking with, how can we turn a graph into a vector? Like that's sort of like the simple problem formulation that we're trying to solve here. So let's think about this for a sec. So we have here, right? And then we said we have node level features. So we have one like node level features, and then we have edge level features. So how are we gonna deal with this? So the like sort of a simple idea, and you know, like this is just, so you can think of this as pseudocode, but it does end up mapping very closely to what Spektral does. But it'll help, and I think it'll still help you understand everything that's going on. So basically, what you do is like you go like, well, for each node, I'm gonna basically look at the node level features. Okay. So first off, like let's say I'm gonna create like some sort of container that says this is the, like, I'm gonna call this like the graph representation, and let's say this is like some vector, right? Like it's a list. And so what I'm gonna do is I'm gonna say, well, for each node, I'm gonna look at the node level features, and then I'm going to aggregate node level features with edge level features plus neighbor node features. Let me just sum this up. Let's expand this out. Yes. So I'm going to aggregate all the node level features with the edge level features. And then after this aggregation, I basically create a node representation. And then I append, so the graph representation dot append the node representation. And then you just like return the graph representation. So this is sort of like, you know, while this feels like very high level pseudocode, like it does actually map, like I said, very closely to what these libraries do. And so we'll just go over some actual code to see how this all works. But like I said, so just to reiterate if this wasn't clear, you want to turn a graph into a vector. To do so, you iterate over all the nodes of the graph. You look at all of the node level features. You aggregate those with the features of its neighbors and its immediate edges. And then you sum up all of these aggregations. So now, like, you know, you may have a bunch of questions here. Like, well, why don't I aggregate like 2 neighbors away? Why am I just aggregating 1? Or like, why don't I aggregate all of the neighbors? Or why am I only aggregating, like, why don't I just aggregate the nodes? Like, why don't I aggregate just the edges? Or why do I not aggregate like the 3 most important edges? All of those are great questions, and the answer is that people actually end up doing all of them. And all of these map to different algorithms which are implemented in Spektral. So for example, So if you go to the spectral documentation here, like, the sort of simple model I described was graph convolutional networks. And so it's called the convolutional network not because there's a convolution operator, but because to build a global representation, you're only using these localized features. And so then, when I talk about the aggregation here, this actually maps roughly to the pooling operation. So you may say well, I want to aggregate the top 4, like the ones with the most features or the most relevant features, or I want to have an attention, or as opposed to aggregating, I want to sum them up, or instead of summing them up, I want to do an average. Like I said, all of these are completely valid. As far as I know, all of these papers all claim to do the best job here. And so it's just up to you to decide what works best for your application. But the nice thing about using someone else's library is that you basically swapping out these different aggregation and pooling mechanisms essentially corresponds to you just changing 2 different parameters in your algorithm. And then depending on the actual data set that you're working with, you can for yourself decide what's the best thing to do. So like I said, so basically a sort of a summary of what I just described, your why is this not? So your choice of aggregation and append mechanism determines the graph neural network algorithm you're using. So these 2 choices uniquely determine the algorithm you're using. And of course, obviously, there's a third one, which is the actual data set that you're using to do some sort of interesting prediction. So, enough talking. Let's just do some coding. So I'm gonna go over the main example that I saw Daniele, let me see, Gratarola implement. So I really recently listened to Daniele give a talk about using the library, and what really struck me is that he really made it a point to make this a sort of reality, which is he mostly thinks of graph neural networks as a way to pre-process graph-like data into vectors or matrices such that you can understand them via a deep learning library. This is not true, for example, in other libraries. Let's say the most popular deep learning library for graphs, I believe today, is called PyTorch Geometric. And so I actually really this is the first library I got exposed to when I was trying to learn more about graph neural networks. But the thing that struck me is that even before you can actually use this library, when you come in, you actually have to come in and install all these libraries by the sparse CUDA libraries. This failed quite a bit, and I actually couldn't even get it to run on stream, if I remember correctly. And so, as opposed to just needing these really specific libraries by CUDA, and having a dependency on them, what if we could just treat the graph neural networks as a data pre-processing step? In which case, it's a lot easier for people to experiment with them as long as they have some basic knowledge of deep learning. So let's go over the example. So the example we're going to be going over here is in examples, and so we're going to be doing some sort of graph prediction on QM9. So let's look at the description. So it's saying here, this example shows how to perform regression of molecular properties with the QM9 dataset using a simple GNN in disjoint mode. The main training loop is written in TensorFlow because we need to avoid the restriction imposed by Keras that the input and output have the first same dimension. This is all fine and good. So let's just get started. We can just come in and import all these libraries here. All right, so these are all of our imports. Let's just give this a second to load. And let's kind of look at a high level what's going on. There's nothing crazy. We have NumPy, TensorFlow, model selection to do training and splitting, the dense layers for Keras, the mean squared error for our loss, the model the model API which will let us actually run model.fit or model.train, I assume, Atom Optimizer because it's faster than SGD, the data set that we're going to be working with QM9. So in particular, one thing I really like about this about the Spektral library is that it just comes with a bunch of data sets in by default, and so we can I believe, where would they be? Yeah, so data sets. So we see there's QM9, there's there's MNIST, there's the linear stuff, there's the graph stage, which I believe is like sort of a math library. So all sorts of libraries, and you know, you just like some sort of citation database. So yeah, like when you think of citations, like they have a sort of graph-like structure because people cite each other's work, and then researchers cite each other depending on their work. Delaunay, I believe, is the triangulation algorithm, if I'm not mistaken, or a way to map stuff into D-space. But you know, like I said, the main one we're going to be looking at today is QM9. So I'll just kind of give this a very quick look. So what they do is they download it from the DeepChem project. So DeepChem is sort of the, like, I would guess like the gold standard for libraries that do anything with like molecular chemistry. And so you can see here that there's node level features, which is the atomic number. So that corresponds to which atom is this. So it's an ID. There's the charge. There's the coordinates, and then there's the ISO, so spin. Is it spinning up or down? And then there's some edge level features. I don't know what these mean, like type and stereo. That's all fine. I don't think we actually need to understand this. And so then if you actually look at the data set, nothing really interesting is going on. So basically, they just load it from a format into an SDF format, and then they just download the data and save it locally. So that's the main thing. So really, like, you know, often, you know, if you're interested in building like a data loading library, like that's pretty much the main thing you need to do, is just like provide like a way for people to you know, import in a data set from abroad, turn it into a CSV or an NumPy array or a pandas array or whatever, and then it makes it really easy for people to pre-process it. So, okay, so great. So now that we've talked about like the data a bit, you know, if we keep going here, we have these layers, and then we have this thing called the edge conditioned convolution. So the way to think about this is, you know, here when I talked about aggregating node and edge level features, so like it's just a way to basically say I have edge level features that I want to aggregate over, and then, you know, here there's some basic stuff like one hot encoding to label. So this is something you'd see in any sort of typical Keras library. And then the last thing, and I'm going to be talking about in more detail, is this NumPy to disjoint representation. So let's talk about this representation for a second. So typically, you know, if you have a graph, like typically, like computers don't understand these sort of 3D graphs. Like the way we work with graphs in computer science is typically in this format called the agency matrix. So the agency matrix is just a way to represent a graph as a matrix. And so you can think of it as each node or column like maps to an edge. And then each edge will also have some ID. So basically, let's say there was no node level features, you just had connections, then the labels in the graph, in the matrix, would just be zeros or ones, depending on the location. Otherwise, you'll have the actual value for it. And so let's say you can turn a graph into an agency matrix. You can turn a graph into an agency matrix like this. But typically in deep learning, like we have a tendency to always work over graphs. And so let's say, you know, we had a matrix like this. And we want to turn this matrix into, but like we don't have just like one molecule, like maybe we have like 100 molecules that we're working with. And so typically what we'll do is that we'll basically put these matrices on each other's diagonals like so. And so these matrices, like the reason why we do this is because it lets us append matrices that are of different sizes. And then at the very last step, like here, for example, I'm just going to make this smaller so that it's clear. So let me delete this. So let's say we had these three matrices here. So you come in, and because let's say you know that the size, I mean, let's work this out, right? So here the size, like this is, each matrix is of size 6 by 6, right? And so we basically align them like so. And so what's going to happen is that this, so here we're going to have 6 plus 6 plus 6. So this total thing here, this line is going to be of length 18. And similarly here, we know that this line is going to be of length 18. So even though we had a couple of graphs, all of a sudden, we were able to combine all of these graphs into a single matrix that's of dimension 18 times 18, right? And this is great because it means that like now instead of feeding these examples one by one, we could just feed like our entire data set as a single step, or feed like batches of our data set to a deep learning algorithm and then do deep learning on these graphs. So like basically now, like we said earlier, like Keras takes this thing and then either produces a classification or a regression or what have you. So one thing you'll immediately notice though, and you know, if you've worked with any sort of high level like you know like even any sort of like high performance computing, is that this matrix is incredibly sparse. So like everything here is going to be 0 and everything here is going to be 0, which basically means like if you're trying to load this thing into deep learning, like onto a GPU, like GPUs typically struggle with this stuff because they can't effectively work with sparse data. And so that's also part of why at GraphCore I'm interested in benchmarking some of these guys on IPUs to see if we can get rid of the sparsity constraint or like basically turn the sparsity into a strength. But this is just something I want to make you notice, like, is that the fact that most of this matrix is actually sparse, and it's going to be sparse everywhere here, sparse everywhere here, and sparse everywhere. So about half of it is actually just all zeros. So that said, there are ways to deal with sparsities with matrices. It's not like there's no solution here. So for example, the main way you deal with it is with this this representation called the Ku representation, so the coordinate format. At a high level, there's no black magic going on. It's basically, as opposed to treating an adjacency matrix like a matrix, you treat it like a dictionary, and then you can do matrix multiplication on these dictionaries directly. And so this is sort of a very common trick that's used a lot in any sort of high performance computing where sparsity is necessary. And if anything, like most data sets are sparse, so odds are most deep learning libraries will use all of these tricks. So great. So now that we have the basics ready, we can just go back to our example. Like we know, so for example, even Spektral has this really nice documentation page where they go over, for example, like the different convolution mechanisms, as in the different ways to collect data from your neighbors. They go over different pooling layers, as in the different way to aggregate data over your neighbors. And they all have, like, you see, like there's averages, there's max, you could do some attention, you could do some sort of sorting over your neighbors. As far as I'm concerned, these are all particular cases. Like there's no a priori reason for me to say that one's better than the other. It's just that we don't know, and you have to try a bunch on data and see what actually works best for your use case, depending on the characteristics of your particular problem. And in particular, the thing I want to show you here again is that if you look at this, so this is what we talked about with this adjacency matrix, is that it's mostly a sparse matrix. And let's say the blue areas are areas where there's connections. So these are the nodes that are actually present in our graph. And the way we turn this into one giant graph is this disjoint union. And so you'll see here in this, let me zoom in. So in this disjoint union, you'll see here that we've appended all of these graphs along their diagonal. And then this other matrix here is to just keep track of the node attributes that we have in our network. So this is just a way for us to say, well, you know, blue are all of the nodes in graph 1, green are all the nodes in graph 2, and so let's say these could be two different molecules, right? Let's say one's cyanide, one's water, and then one's, I don't know, sulfuric acid, for example. And this also helps because you may have, like, let's say some node level features that you have here. You could also have like a separate matrix like this for your edge level features. That way you have a dictionary where you can quickly get these results. And here, like I said, like yeah, so I've actually talked about RDKit before in a past stream, but basically, given that we're working with molecules, you can basically use its preprocessing libraries to turn a molecule into the Smiles format. The Smiles format is basically a way to turn a molecule into a string. And then once it's a string, you can turn it to, you can, let's say, use any sort of NLP technique on top of it, whether it's transformers or RNNs or hidden Markov model. Like any sort of sequence-to-sequence algorithm will work just fine here. So yeah, you'll see our other things, like let's say as opposed to you custom having a dictionary of all the atomic symbols for each molecule, like you have them built in, and then the spin, and then what's the valid score for this molecule, as in something like how likely is this molecule to exist in the real world, and this may have different heuristics for it. It could be some domain knowledge built by chemists and physicists. Like one thing that makes working with some of the stuff harder is that if you don't, like in my case, like I don't have domain knowledge in chemistry or biology, like I can't read proteins and molecules. It makes it harder for me to debug the outputs of my model without having some other expert come in and look at it and tell me, like, does this make sense? Whereas in English, like because I'm a native speaker, I can come in and I can be like, well, like this looks like a meaningful sentence, or this doesn't look like a meaningful sentence. So back to the example, like we said, we want to do a graph prediction over the QM9 representation. And so, okay, so there's some learning rate parameters. Great. Like, so far nothing looks weird. Like we just have a batch size, like 32 is just a very common one. Epochs means we're, going over the data 10 times, and we have some sort of small learning rate. Like these numbers could be arbitrarily different and it wouldn't change all that much. Right. And so now the first thing we're going to do here is we're basically going to create our input data and our output data. So let's do this. So first off, like it's going to be downloading the QM9 data set, and it looks like it's downloading it from the DeepChem AWS server. So it's reading the SDF format. So let's just double check what's SDF format. So the spatial data file, so it's a single user geodatabase file by Autodesk. Oh, interesting. Okay, this is done. So let's see what happens if I put a. All right. So you'll see here, like this is a gigantic matrix, right? So maybe just printing it out wasn't that useful. So let me just print out the shape. Right, okay. So basically this is telling us that there's 1,000 molecules here. And so what happens if we look at Y? Sorry, let's say Y.shape. Right. And it's of size 1,000. So that means like we have like 1,000 labels for our 1,000 examples. And so there's a couple of nice things you'll notice here. So for example, here it's telling us like, well, we want our return type to be an NumPy array. We want you to use the atomic number as the node feature. We want you to use the type of the edge as its edge level feature. And notice, like I talked about earlier, like these could be all sorts of stuff. We said it could be the spin, it could be the charge, it could be whatever you want. We don't want to pad it. We don't want it to do a self loop, and then we just want 1,000 of them. And here, for example, given, like, remember I said that you can do, once you set your problem in this framework, there's a couple of stuff you can solve. But here, for example, we're trying to understand the heat capacity of a molecule. And so we're just going to be looking at the heat capacity feature. But like I said, we could be looking at all sorts of stuff from solubility to toxicity to photovoltaic response, or any sort of biological property or physical property that you think is interesting. So okay, so it looks like there's some more pre-processing here. So let's just see what's happening. So looks like first off, we want to make sure that our nodes and edges are all unique, and then we want to give them all a one-hot encoding. Okay, that all sounds reasonable for now. And then we want to basically set up our test and split data. So how does this work? Our train, test, and validation data. So that's why we have it split up like this. So A train, A test, X train, X test, E train. Okay, yeah. So, oh, I see. Okay. So usually, like this would be in any sort of deep learning algorithm, you would have like you would have your nodes. Sorry, you would have your X and you'd have your Y, like your input and your output. In this case, however, we have we have the agency matrix. So that's what the A train, A test is. We have the node level features. We have the edge level features. And then finally, we have like our labels. So that's why like this looks a bit longer than usual. So right, so then we come in and we build our model. So here in this case, I'm just gonna copy paste this model here. So we're saying like, okay, as an input, we have X in, And then for A, we're saying, yeah, so we're literally just setting up each one. We're saying, actually, what's is input? I forget what this is. So TensorFlow, Keras, layers, input. Let's just double check I understand what this means. So it's used to just instantiate a Keras tensor. Okay, sure. Like it's sure. Okay. So yeah, typically this would look a bit simpler because you would have one input, but here in this case, because we have we have 1, 2, 3 inputs. And the segment IDs, so actually 4 inputs. It looks a bit more complicated. We do this edge level condition convolution. So this is like the batch number. Activation is ReLU, but it could be anything else. Then you do this global sum pool, and then you finish off with a dense layer so that you can actually do a regression. You set up an optimizer with Atom with your learning rate, and then you look at mean squared error given that it's a regression. If this was a classification, you would use the categorical cross entropy, for example. And so like looking at this, you'll see here that here it uses xn, an, en, and then the edge condition convolution here at x2 uses x1, an, edge n, and then x3 uses x2 and in. Okay. I may need some more time to understand exactly here what they mean by like the segment IDs, but I'm assuming like it just means, oh, I see. Okay. So okay, yeah, so it's sort of like the one-hot encoding for the edge. And then separately from the one-hot encoding for the edge, we also have the feature for the edge, which is actually its type. So that's why we have 2 edge-level features, and that's why we're doing this thing, even though it seems a bit convoluted. But basically, like, each of these is an input to the next. So like x1 is an input to x2, x2 is an input to x3. And then, we feed this in, and then we finally do our output prediction. So this is sort of like the basic model structure. And so then here, what they do is they set everything up in a TensorFlow function. So what's interesting, so this is actually, here, I will do this. So I actually learned about TensorFlow function fairly recently. But here's the thing, given that we're coming in, you'll see here that as opposed to just using model.fit, we're actually explicitly creating the state structure. And what this is it'll let you, it'll basically give you a context where you can actually get the loss back from your model, sum up all of these losses, put those losses back on your tape. That way you can apply backprop to it. And so the idea is because these aren't custom, this isn't sort of just the standard model, you need to basically set up your own backprop here. That said, once you've done this once, you don't need to really come back and do this again. Let's say if you come in and completely changed your node level features, your edge level features, your indexes, all of the above, you don't actually need to change this. So this is just code that you end up writing once. So a TF function is also interesting. Like I was saying earlier, it's a function whose existence I learned about fairly recently. So let me just show you what it does. But I've been using it quite a bit lately. So basically, new TensorFlow is dynamic in the sense that you don't know, you're basically giving the TensorFlow compiler a hint that, look, this is going to be a function that I want that I want added to the graph. It's not a function that's going to change its structure. What's going to change is its input and output. Therefore, I want you to compile it and run it really fast, and then, freely distribute it over multiple GPUs or CPUs or IPUs or, whatever you're working with. It just all works out of the box here. And so then, when we come back here, you come in and you're like, okay, well, so far we just set up the training loop. We said how a single training step works and how we should do backprop, but we didn't actually feed it batches of data. And so this is what we're going to be doing next. So you come in here and you say, well, my current batch is this. This is how many batches I have in this epoch, which is the length of my data divided by the number of divided by the size of my batch. You set up like a batch iterator. So that way, like when you say for B in batches trained, it'll just at every step give you the next batch size. You turn your data to this disjoint format such that you can take all of your disjoint graphs and add them to this one giant sparse graph. And then you do a single training step. Once this training step is done, you record the loss, and then you add it to your batch, and then at the very end, you report the last loss that you get. Model.loss equals 0. Yes. All right. So finally, like at the very end, like you come in. See, look, so right now it's already fitting the model, and it doesn't run for very long since it's a fairly small data set. The loss keeps going down. It still looks like it's fairly high, so I wonder if we could make, this may consume a lot, yeah. So converting a sparse index slices to a dense tensor of unknown shape. So this was earlier when I was talking about this here. Like, even though you were able to fit everything this way, like the fact is, like most of this matrix is going to be really sparse. And so then when you try to feed this thing into something like Keras or TensorFlow, it's going to complain like, look, this is really sparse and it's going to take up a lot of memory. In this case, we just used 1,000 molecules, but let's say imagine you're using a couple of million and each of those molecules are very large. This would quickly become not so scalable. So like I said here, so, you know, we come in here and then we see like the final loss. And I think that's pretty much it, right? And so let's just make sure that we you know, let's say like just go over some loose ends. So here, for example, like I talked about this already, like, you know, like we're just setting up like all of our inputs given that we have several of them, whereas in typical machine learning models, like you usually think of it as having a single input. That said, this is not irregular. Like let's say you're doing, I don't know, you're looking at, let's say, like the output of like the input from 2 sensors of yours, then you can have like basically 2 different input shapes and then feed both of those inputs to a model and then do some classification on both of those models. So what I really like about this sort of functional style of working with TensorFlow is that you aren't limited by just this like single input, single output domain. You can have multiple inputs, multiple outputs, and then as long as you have a well-defined loss function, you can do whatever you want. So in this case, it's multiple input, single output. But you could have like all sorts of schemes here. So in this TF function here, like what they're doing is that he's basically defining the data type for most of the stuff that you're going to be working for, basically this here. So here you're saying like X is going to be a data type consisting of floats. So they're all floats except the third one. And the reason that's the case is because this is I, which is the edge index. So this is going to be integers. And so that's why they're using int32s here. And they're also setting up the size, right? So they're saying like, well, we know in this case that it's going to be a tensor of size f. So let's see, where is f, for example, in this case? Is it somewhere? F. Why am I missing this? Okay, so it was used here. Oh, okay, here. So, okay, so yeah, I don't know about these names, but it's just like f is the number of basically the dimensionality of your node features, and then e is the dimensionality of your edge features. So what this -1 means here is it's gonna basically look at the size of the largest of the last one, like so the largest one, and x0 means it's gonna be looking at the like basically like the first element of a list, and then look at the last element in that list. And then like we said, so this is dimensionality of the target, so that's all fine. So we could just have had these like as is, like here, for example, but I guess it just makes things a bit cleaner. So let's say in the case here, like in X's case, like these are node level features, and so it's a vector. But in the case of A, this is an adjacency matrix, so this is going to be a sparse matrix because it's an adjacency matrix, and so that's why it's none here. And then here when you come in, this is going to say, okay, well, this is S, and we said this is the dimension of edge level features. And so this basically makes it so TensorFlow can run your training step very efficiently. I wonder what happens. Like if you just remove this thing, what would happen? Would it not run or would it run slowly? Okay, it's running much more slowly, but the loss is smaller too, which is pretty funny. Let's try this again. Oh, interesting. It's checkpointing from the old point, I guess. So that's why the loss is reducing. So it does seem like more steps would help this converge. And so I guess as a sort of very simple thing here, like let's just look at the number of epochs. Number of epochs. I mean, I'm just going to make this like, let's say 1,000. And let's just look, let's see if this actually goes down all the way to 0, for example, or if it still hangs. But you see here, like I'm not doing anything special, I guess. Like the main thing I want to get back to is like, the picture here that we described was actually very simplified, pretty accurately describes like how to work with a lot of these algorithms. And so this is like a sort of a final high level overview. We come in here, we load our data, which in this case is the QM9 data, which is a molecular data set. And we're doing a regression to figure out the heat capacity of a molecule. We make sure that all of the node level features and edge level features are unique. We keep track of the total number of node features and the total number of edge features. We create our train and test split. We create our model, which has multiple inputs, like one for the adjacency matrix, one for the node features, one for the edge features, and one for the edge segment IDs. We create our model, which in this case is an edge condition convolution with a ReLU, and we chain the model and then we do a dense output. We optimize with Atom, and then we just take the mean squared error because it's a regression problem. Because we want this to run efficiently, we can decorate our training step with a TF function where we specify the dimensionality of each of our input and output data sets. Then we set up our own custom training step where we have our own gradient tape so that we can keep track of the loss functions. After that, we start feeding the data in via batches. We feed all of the matrices in a format called the disjoint format, which essentially lets us turn a bunch of sparse adjacency matrix into one really giant matrix that we can feed in one go. TensorFlow will complain that this is very sparse, which is why there's potential to make this more efficient with something like the COO format or using a different hardware infrastructure like the IPU. And then you come in here and you basically record the loss that you get per batch and you report it. And that's pretty much it. Like that's how you do graph neural networks. So thank you so much, everyone. I was super glad to do this episode. Turned out to be a lot simpler than I expected. So stay tuned. I'll probably do like another similar episode about some other workload in drug discovery or pharmacology next week. Thanks again. And if you enjoyed this, like please subscribe or follow me on Twitter where I'll post like more of my thoughts in shorter form. Thank you.